Good afternoon, learners. I am Dr. Munish Bharadwaj from School of Engineering and Technology. As you remember, we were discussing about the design of steel structures. In that course, today we will discuss about the design of riveted connections or riveted joints. As you know, the question first arises, why a connection or a joint? You know that in steel structures, the material, basic material is available in certain lengths and sizes, and those lengths and sizes are not enough or sufficient, so that by using a single member we can construct a build. So we have to join two structural members to form a particular structural member, like beam, column, that way. So whatever material is available in the market, which is produced by the companies, these steel making companies, these rolled sections are prepared by these companies, and these are available in the market. So from those which are available in the market, we will use different members and connect them to give the proper size and shape of the required structural element. So because of that, we need the connections or the joints through which we can make a structural member by using the material available in the market. Now, what is the importance of a connection? You should keep in your mind that connections are as important as the main member, because if one fails, then basic purpose of the connection or the structure fails. Means if the member fails, then our structure fails. Also, if the connection is failed, then also our structure will not fulfill our purpose. Means it will not be serviceable. So here you see that joint as well as the member, structural member, both are important. So joint, in that way, the joint is very important thing, connection is very important thing in the structure, and we should take all care to properly design and make a connection in the field, so that our structure fulfills our service or purpose. Now the question arises that what type of connections are there? So based on the different devices used or different things used to make a connection, we can divide the connections into three categories. First is riveted connection, in which we use rivets to make connection. Second is bolted connection. In these type of connections, we make use of bolts. And third category is welded connections. As the name indicates, we use welds to make such type of connections. So basically there are three type of connections: riveted, bolted and welded. Now, what type of forces acts on the joints? We know that connections are of three types. On any of the type of connection or on any connection, what type of forces act. So these are the four forces here. As you see, one is direct shear, means the force which is uniformly distributed over the connection. Second is eccentric shear. In this case, the point of action of the force does not coincide with the CG of the connection, center of gravity of the connection. So because of that, point of application is away from the center of gravity of the connection. So here there is an eccentricity of the application of load with respect to the CG of the connection. So that is why we call it as eccentric shear. What is direct tension, in which tensile forces acts on the member, and fourth is bending moment. When eccentric load is acting on the connection, then there will be two things there. That direct shear will be there, as well as movement. Because of that load into the eccentricity, that movement will also come into the picture at such type of connections. So these are the forces that acts on the joints. Now we were talking about the riveted joint. So with this much of an introduction regarding the connections, now we come to the main topic, which is the riveted joints. So let's see what are the classification of the rivets. Rivets that we use for the connections may be of three types, and these are based on the driving methods. That for driving of the rivets, which method is used, so based on that this categorization is done, and there are basically three categories based on these driving methods. First is power driven shop rivets. As it is clear from its name, these rivets are power driven, and this is done in the workshop. Second is power driven field rivets, means such type of rivets are power driven, but riveting is done in the field at site. Third type of rivets are hand driven rivets. Here we are using hands, means handhold devices we are using, just like hammer we are using, and no mechanical device is used here. So these are the three type of rivets basically. Code says that, as I told you, if you remember, that IS 800 is the relevant code to this particular course, and you should have with it when you study this particular course, because the codal provisions are very important, and those codal provisions you have to refer from time to time in your design. Now here the code says that power driven shop rivets are better than the other two categories, and in such type of rivets we can go for higher permissible limits, because here we can ensure a better quality control. Because of that better quality control, this type of riveting is the best type of riveting, and we can go for little bit higher permissible stress limits for such type of rivets. Second best type is power driven field rivets. Here these rivets are power driven but done at site. So here the quality control may be little bit less in comparison to the power driven shop rivets. So here the permissible stresses will be little bit less in comparison to the power driven shop rivets. Third type, which is the hand driven rivets, here we cannot have that much of quality control as in case of power driven shop rivets and power driven field rivets, and because of that, in such type of rivets we take lesser permissible stresses in these rivets. So these are the types or the classification of rivets. Now some terminology related to the riveting. First is nominal diameter of rivets. Nominal diameter is the diameter of a cold rivet measured before driving, because you know for driving we are using power as well as hammers, so while driving there will be certainly a change in the diameter of the rivet. So here nominal diameter refers to or indicates to the diameter of the cold rivet measured before driving. Mind it. Second terminology which is generally used in that riveting is the gross diameter of rivets. Gross diameter of the rivets is the diameter of rivet measured after driving, and generally the diameter of the hole is adopted as the gross diameter of the rivet, because ultimately that hole has to be filled with the rivet, because rivet will occupy the whole space of the particular hole driven in the any plate for connection. So here gross diameter is taken as the diameter of the hole. Now code says that for arriving gross diameter from the nominal diameter, add 1.5 mm for the rivets having nominal diameter as equal to or less than 25 mm. In case of rivets having nominal diameter more than 25 mm, then add 2 mm to the nominal diameter to get the gross diameter, as it is shown here that D equal to Dn plus 1.5 mm for Dn less than or equal to 25 mm and D equal to Dn plus 2.0 mm for Dn greater than 25 mm. So that is the way how we calculate the gross diameter of the rivets from the nominal diameter of the rivets. One important terminology that is used in riveting is pitch of rivets. Pitch of rivets as you see in this figure is distance between two consecutive rivets measured parallel to the direction of force. Here this thing is very important, direction of the force. Here this is one connection shown to you. These are rivets here in two lines. This is 3 rivets in one line, 2 rivets in another line. This P is the force acting on this connection. So distance we have to measure here should be parallel to the force applied on the connection, direction of the force applied on the connection. So here as you see, this distance parallel to this force P is this distance, which is shown here as S. So here this distance between the two rivets, consecutive rivets, in the direction parallel to the direction of the force is S, and this is called as the pitch of the rivets. Another terminology which is very important in riveted connections is gauge distance of rivets. What is gauge distance? This is also a distance between two consecutive rivets, but here it is transverse distance. and measured at right angle to the direction of force. Direction of force is here this direction of P. This G is representing here the gauge distance, which is at right angle to the direction of the force. So here you can see the pitch and gauge for rivets in a particular connection. So these two terms are very important, which you should remember, because these will be used very frequently in all riveted and bolted connections. Now, before actual design, let's move to the assumptions. Let's see what assumptions we take before for designing the connections. First assumption is friction between plates is neglected. In actual practice, you know that when there are two plates or of the same material or of different material, there will be certainly little bit friction. But here, for design of riveted connections, we assume that friction is zero, friction is neglected. This we do for the simplification of the design. Otherwise, if we take into consideration the friction also into picture, then our design will be little bit tedious. Second assumption is shear stress is uniform on cross section of rivet. Shear stress, as you know, there is a shear distribution of shear stress. You have studied in your strength of material course, but here for design purpose, here we assume that shear stress is uniform across the section of the rivet. There is no variation of the shear stress across the section of the cross section of the rivet. Third is distribution of direct stress on the portion of plates between rivet holes is uniform. When we are considering the rivet holes here, then we assume that the distribution of the direct stress on these holes is uniform. Fourth assumption is rivets in group subjected to direct load share the load equally. When there are more than one rivet in a connection and that connection is subjected to direct load, then in that condition we assume that that load is equally shared by the all rivets. Next assumption is that bending stress in the rivets is neglected. Here it is very important assumption that we are neglecting the bending stresses in the rivets. Next assumption is rivets fill completely the holes in which they are driven. There may be little bit gap because of the non-uniformity of the hole or the non-uniformity of the particular shape of the rivet. So in that case there may be a little bit gap, but here for design purpose we are assuming that rivets fill completely the holes in which they are driven. Now these assumptions we take for simplification of our design process, and these are approximate and these are not absolutely correct. But while taking these assumptions, we always care that adoption of these assumptions leads to a safe design. Means assumptions that we are making should not lead us to a faulty design or a design of a structure of a connection which may fail. So these assumptions lead us for a safer design. So till these assumptions lead us to a safer design, then there is no problem. Now let's talk about the types of riveted joint. There are two types of riveted joints. Means in two situations the joints can be made. First is lap joint and second is butt joint. Now let's see what these lap joint and butt joints are. As it is clear from the name, lap joint means overlapping. If this is one plate, this is another plate, and I have to connect these two plates with the help of rivets, then what I will do, I will overlap these, put one over another, and then put a rivet there. Like rivet will go across the two plates. So this is lap joint. Second type of joint is butt joint. In butt joint, the plates are put face to face in contact, and then now you think that how we can join these, because there is no overlapping here. So what we will do, we will put cover plate either on one side of these two plates up, or on both sides, up and down both sides. So by putting cover plates, which will go the part of the plate on this plate and part of on this plate, so cover plate will be put on either on one side or on both sides, and rivets will be driven one this side and one this side. So these are the butt joints. Now lap joint. Lap joint may be single riveted if only a single line of rivet is provided, or these may be double riveted if a double line of rivets is provided, then it is doubly riveted. Doubly riveted based on the fashion in which the rivets are provided in the connection. These can be of two types, chain form and second zigzag rivet lap joint. In chain form, rivets are provided in a single line, in a line, and in zigzag, as it clears it from its name, these are provided in zigzag fashion in the connection. So these are the two types of the lap joint, single riveted and the double riveted. But of course the butt joint are also of two types, as I told you earlier, based on the cover, that cover is on the single side or on both side. If the cover is on single side, then this is single cover butt joint. If the cover is on both sides of the plates, then this is double cover butt joint. So this division or classification is based on the cover. Now let's talk about what are the different methods of failure of a riveted joint, because without knowing that in what fashion or in what way the riveted connections or joints fail, we cannot understand the method of design, because the design has to be in accordance with the failure pattern. If we once know that how the connection fails, then we can take the proper steps to design a proper connection. So here you see four types basically. One is shearing of rivets, in which a rivet is sheared off under the load. Second is tearing of plates. If the load is excess, and you know that for providing the rivets we are making hole in the plate. So at that line of rivet, in that connection part, the strength of the plate decreases because of these holes. So if the load is more than the permissible limit, then tearing of plate may occur. Next is bearing failure of rivet. On the diameter of the rivet, the bearing failure may occur because of the excess load. Next type of failure is which are caused because of the lack of the proper or appropriate edge distance. And in this particular case, there may be three types of failures: bearing, splitting and shearing. And that is because of lack of the appropriate edge distance. So this is bearing, splitting and shearing at the edge of plates. So these are the basic failure patterns in a riveted joint. So while getting answers for appropriate design, we have to keep these failures in mind, that how the rivets fail, how a plate fail, and we have to give the adequate strength to the rivet or plate, or we have to take these, we have to keep these things in our mind while designing a connection. Now first we take the shearing of rivets. Rivets are sheared across their cross-sectional area. If this is a single rivet, then under the load this rivet may be sheared off, and this shear failure of the rivet may be of two types: single shear failure, if the rivet is failed at one cross section, or double shear failure if the rivet is failing at the two cross sections. Means rivets is sheared off at two cross sections, then double shear failure. If it is sheared off at one cross section only, then it is single shear failure. Now under the load, what will be the resistance of rivet in single shear? Resistance of rivet will be the effective area in bearing that shear force or shear, direct shear, into the shearing stress of the rivet. So if we take this, if we look at this formula, this Fs is the shearing resistance of rivet. This is equal to pi by 4 d dash square. D dash is the gross diameter. So this pi by 4 d dash square gives us the area which is effective in taking the shear stress into the permissible, maximum permissible shear stress, which is shown here as tau Vf. So if we multiply this permissible shear stress into the effective area, then we get the shearing resistance of the rivet. Now let's talk about the tearing of plates. What happens, as I told you earlier, that because of making holes in the plate for making connection, the strength of the plate decreases and rivets are driven into these holes. So when the load is excessive, when the strength of plate is less than that of the riveting tear of the plate, then that of the limit, permissible limit, then what happens? That tearing of the plate may occur that way. And resistance to tearing we can calculate as Ft equal to B minus D dash. B is the width of the plate, D dash is the gross diameter. We are considering that one hole is made in the plate, means one rivet is there. So B, width of the plate, minus D dash, means now that D dash area has been subtracted or deducted. So this is the effective width of the plate to take this load into T. This is the effective area now. T is the thickness of the plate into sigma AT, which is the allowable tensile strength of the plate. So if we multiply the allowable tensile strength of the plate to the effective area of the plate, which is B minus D dash into T, then we get the resistance to tearing for the plate. Now let's talk about the bearing of rivets. What happens that under the load, when the load is excessive, what happens? Rivet is crushed by the plate due to large pressure on the area of the contact of rivet and the plate. So the area where these in contact, what these rivet and the plate, so because of the excess pressure, rivet is crushed, and this such type of failure is bearing of rivets. Here we can calculate the resistance to bearing for the rivets by using this formula FBR, which is bearing resistance, equal to D dash into T. Now this is the projected area or the effective area to the bearing resistance, to the bearing of rivets. So D dash into T, where D dash is the gross diameter of the rivet, T is the thickness of plate. So this is the effective area into sigma PF. Sigma PF is maximum permissible bearing stress in rivets. So if we multiply the maximum permissible bearing stress in rivet to the effective area of the rivet, which is effective to take the bearing stresses, which is calculated as gross diameter into the thickness of plate, then we get the bearing resistance of the rivets. Now bearing, splitting and shearing of plate. These three types of failure may occur due to insufficient edge distance, as I told you earlier. So what is the remedy? Remedy is that provide the proper or appropriate edge distance while you are designing the connection. Minimum edge distance is taken approximately as 1.5 times the gross diameter of the rivet, or this is an approximate idea. Also IS code 800 gives these appropriate edge distances. So you have to refer the code for the appropriate edge distance while designing the connection. Now, with this much introduction of the failure patterns, now let's move to some other important terminology and their permissible limits, minimum maximum limits. Pitch, as you know, this is the distance between the consecutive rivets measured in the direction of the force. Code says that minimum pitch should be 2.5 times the diameter of the rivet hole, means 2.5 d dash, and maximum pitch, as the code specifies, there are two different limits depending upon whether that part is in tension or compression. For tension, code says that the maximum pitch should be 16 times the thickness of plate, 16 T, or 200 mm, whichever is less. In case part is in compression, then in that case the maximum pitch is 12 times or 200 mm, whichever is less. So these are the limits to the pitch. Code also specifies working stresses in rivets. Here in this table, for two cases only, these working stresses are shown. First is direct tension in case of direct tension, and second in case of shear. So I have shown you here the part of the table. The full table is given in your IS 800 code. So let's see here some cases. In direct tension, code says that power driven shop rivets can have the working stress as 100 MPa. Power driven field rivets can have working stress as 90 MPa. So as I told you earlier, that power driven shop rivets are considered to be the best one. So here you see that working stress as allowed by the code is 100 MPa. In case of power driven field rivets, this is 10% less than that shop rivets, power driven shop rivets, and it is 90 MPa. In case of hand driven rivets, further 10% is reduced and it is 80 MPa. In case of shear also, similar type of values are given by the code for power driven shop rivets, field rivets, and also the hand driven rivets. So I would like to suggest you to go through the IS 800 code and find these different working stress in different type of stresses that are given in the code. Now we have to calculate the strength of a riveted joint. A strength of a riveted joint is the least of the following strengths that we calculate first. First is a strength against shearing of rivets. And as you know, shearing can be of two types, single shear and double shear, and the difference is that in double shear the shearing is at the two cross sections. So for single shear, as we know, the formula for calculation of the shearing resistance or the strength is PS equal to pi by 4 d square into tau VF. In case of double shear, this gets doubled. Another strength is strength in bearing against plate. that, as we just now studied, PB we can calculate as D into T into sigma PF. Third is strength against tearing of plate. This PT can be calculated as G minus ND if n number of rivets rows are there. D is the diameter of the gross diameter of the rivet, so G minus ND into T into sigma TF. So that way we can calculate the strength against tearing of plate. Next is bursting at end of plate, and strength in this case we can calculate as PE equal to E minus D by 2 into T into sigma AT, where E is the edge distance. Rest you know. Next type of strength that we calculate, tension failure of rivets. The strength is PTF can be calculated as pi by 4 D square into sigma TF. So out of these 5 strengths, whichever is less, that is taken as the strength of the riveted joint. Now, rivet value. Rivet value is the least value of the strength of a single rivet in shearing or bearing. So there are two types of failures of the rivet, shearing and bearing. So in these two, whichever is less, that least value of the strength of a single rivet. Here we are talking about a one rivet. So the rivet value is calculated for one rivet or a single rivet. So the least value of the strength of the single rivet in shearing or bearing is taken as the rivet value, and we will require this rivet value when we will calculate the number of rivets required for a connection, because load will be given in the problem and you would be required to design the connection, so to calculate the number of rivets. So that way you will require this value. Now finally, the efficiency of riveted joint. As you know that we are making hole in the plate to make the connections, so strength gets reduced, but we are providing the rivets in those holes. So finally we want to know that what is the efficiency of the riveted joint, and that efficiency is defined or calculated as the ratio of the least strength of the joint divided by strength of solid plate. Strength of solid plate you can calculate, and you can calculate the least strength of the joint. So divide the least strength of the joint by strength of the solid plate, multiply it by 100, you will get the efficiency of riveted joint. So this is all about the introductory part of the theory part of the riveted joints. In next lecture we will solve some problem so that you can understand very well the riveted connections. Thank you.